Welcome to the next lecture of the channel. And in the last lecture we did an introduction class. We did some explanations regarding the conductors, insulators and semiconductors, though they were not enough. Today in details we'll analyze in this lecture 2 session. Also discuss these characteristics in atomic level as well as a materialistic view, using some examples in a materialistic form by analyzing some common conductors, for example copper, silver, and we'll also analyze some of the insulators to show a difference in properties among the conductor, insulators and semiconductors. So let's begin the class. Moving on to conductor. Conductor is normally a material which is capable of moving electric charge through it, and insulator is a kind of material which does not allow the flow of charge through them. So analyzing it in an atomic level, you could see that observing the property of an insulator in atomic level, we can say that it does not have any free electrons in the outermost orbit, but in case of conductor, make them as free electrons. Conductors are the materials which allow easily the flow of current through them. Why? Because these are the materials which are the free electrons in the outermost layer of the conduction band, where it could easily jump in a conductor, the valence band and the conduction band over. So practically the band gap is zero. Therefore the current could easily pass. But in case of an insulator, we have a very high energy gap, and this energy gap is equivalent to nearly 3 to 6 electron volts, which is very high. Even if we apply a voltage of at an order of magnitude of 10 to the power 3 or 10 to the power 4 volts, then also this energy gap or this barrier could not be broken, and this can never be turned into a conductor. But at very high voltage of nearly equals to 10 to the power 8 volts or 10 to the power 9 volts, in certain insulators this energy gap is broken, and that point it is called the breakdown or the voltage breakdown of an insulator. Now in the example of copper, as you could see, the outermost orbit comprises of only one electron, by virtue of which now the property of conductor says that the valence band comprises of very little or 1 or 2 electrons. That is in case of copper, which comprises only one electron in the outermost orbit, which is the valence band. Electrons in the conduction band require very little energy to stay in the conduction band and conduct electricity. So students, now in semiconductors will see that there is a very low energy gap between the conduction band and the valence band. Normally in a semiconductor, the electrons from the conduction band jump to the valence band through this energy gap, and that is called conduction in a semiconductor. And this valence band comprises of holes. So what are holes? Holes are the absence of electrons, an area where electrons are needed but they are absent. That particular concept or property is called holes. Holes is a theoretical concept. You will not see a hole in a microscope, but holes are the absence of electrons. So when there is an absence of electron, that area will have the tendency to attract the electron. So by virtue of this, the electrons jump from the conduction band to the energy band, to the valence band through this energy gap. Normally this energy gap is 0.1 electron volts to 1.0 electron volts in a semiconductor. Typically vary from you may say silicon to germanium. Compared to germanium and carbon, this band gap of silicon is little bit higher. So now, what is the concept of holes and electrons? Why the electrons come closer to the holes? Because normally, as I said, has a tendency to attract the electrons. But why when electrons and holes combine with each other, there is nothing left? Because just imagine this white spot in this black background is a electron, and this is a hole. So if this is called white and this is called black, then this area will also be called, it can be called black, it can also be called absence of whiteness. So when these two combine with each other, it will become complete black. Okay. So when the electrons from the conduction band jump to the valence band, they will be totally filled with electrons. Now we'll move on to the types of semiconductors. As in the earlier class we have discussed, semiconductors are normally divided into two types: the intrinsic semiconductor and the extrinsic semiconductor. Now, the intrinsic semiconductor are the pure semiconductor. As I said, this is a semiconductor. It can be silicon, it can be germanium, it can be carbon, and extrinsic semiconductors. So extrinsic semiconductors can be further divided into two types, that is the P type and the N type. This division of P type and N type from the extrinsic semiconductor is done by virtue of its type of doping. So what is doping? Doping is a process of adding an external impurity, a trivalent or a pentavalent impurity, to an intrinsic semiconductor to convert it into an extrinsic semiconductor. Now, if we dope a trivalent impurity, that is atom with a valency of 3, when doped into an intrinsic semiconductor, it becomes a p-type extrinsic semiconductor. And on the other hand, when we dope a pentavalent impurity, that is an atom comprising of valency of 5, when doped into an intrinsic semiconductor, it becomes a n-type extrinsic semiconductor. A p-type semiconductor is also called a acceptor, and n-type semiconductor is also called a donor, because n-type semiconductor donates an electron, whereas a p-type semiconductor accepts an electron. Now, in the earlier class, I have also said that when a p-type semiconductor and an n-type semiconductor merge with each other, it becomes a P-N junction or a diode. So, in practical case, we do not merge a p-type semiconductor and an n-type semiconductor together. Rather, we take a complete intrinsic semiconductor, might it be silicon or germanium, but remember, in all electronics industry equipments or making an amplifier or a diode, always silicon is being preferred. Why? We'll come to it later. Now, in a intrinsic semiconductor, how a P-N junction is being fabricated? A center line is first made between the two halves of an intrinsic semiconductor. Then this half is doped with a trivalent impurity, for example aluminium, gallium or boron is doped to this particular area of the intrinsic semiconductor, and to this particular area any pentavalent impurity is doped. For example, arsenic, antimony or phosphorus is doped into this area. So when a trivalent impurity is doped to this particular area, it becomes a p-type semiconductor, and when an pentavalent impurity is doped to this particular area, it becomes a n-type semiconductor. So we got a P-N junction. So in theoretical terms, we could say that a p-type semiconductor and an n-type semiconductor are fabricated to form a P-N junction, but in practical industry application, an intrinsic semiconductor partially is doped with a trivalent impurity and the other partial is doped with a pentavalent impurity to make a P-N junction. Okay. Now, observing a n-type semiconductor, you could see impurity arsenic is being added in the process of doping to an intrinsic semiconductor, that is silicon. Now, this impurity is nothing but a free electron contained in this atom, which turns the property of this entire intrinsic semiconductor into a n-type extrinsic semiconductor. Arsenic comprises of 8 electrons in the conduction band and only 1 electron in the valence band. This free electron is responsible to make this entire silicon intrinsic semiconductor into an extrinsic n-type semiconductor. Now moving on to, now in a p-type semiconductor, the impurity is aluminium, which has, observing a p-type semiconductor, we have a silicon, same silicon intrinsic semiconductor where impurity aluminium is being added. Now aluminium comprises of 7 electrons in its conduction band, so there is a deficiency of 1 electron to make it a complete band. Therefore this deficiency is called hole, as I have said earlier. So this impurity, trivalent impurity aluminium having a valency of 3, when added to as an impurity doped into an intrinsic semiconductor, becomes a p-type semiconductor. Now moving on to the working principle of a P-N junction. Now discussing about biasing. Biasing is the process of involvement of current and voltage in activation of a material, a diode into a certain aspect. Bias is defined as the control of voltage or current. So a P-N junction, well, given as I said in the previous lecture, when a positive terminal is connected to the positive terminal of the P to the positive and N to the negative, it's called forward biasing. When the reverse process is done, that is positive end to the negative terminal of the battery and positive end of the battery to the negative terminal of the P-N junction, it becomes reverse biasing. As I said, the P-N junction only conducts in positive direction, that is the forward bias condition. So let us understand one thing, that conventionally the direction in which the electron moves is opposite to the direction of current flow. So if electron is moving from A to B, electrons are moving from A to B, then we'll say that the electricity is flowing from B to A. This is just for a convention purpose, because electrons are negatively charged. So when a negatively charged particle moves in one direction, the opposite direction is considered to be the way of or the vector of electricity. Now in forward bias condition, there is a voltage drop of nearly 0.7 volts. I wrote here minus because whatever voltage you give here, there will be a subtraction of 0.7 volt from this voltage, from the terminal voltage. This, suppose we are giving 1 volt, as we saw in multisim in the previous lecture, we gave 1 volt and we had how much? 0.04 volts, which is nearly equals to 0.4 volts. As we saw in multisim in the previous class, when we give 1 volt voltage, or I think we gave 2 volt voltage and we had 1.4 volts output, that is we had a voltage drop of 0.6 volts. Normally when we use silicon as an intrinsic substrate to the P-N junction, where P and N type doping, or we could say the trivalent and the pentavalent doping has been done on a silicon, then we observe a voltage drop of 0.7 volt. But in place of silicon, if we use germanium, it is seen that a 0.3 volt drop is seen. Therefore, in forward bias condition, therefore in forward bias condition, the voltage difference, therefore in forward bias condition, the current flows through the P-N junction with a voltage drop of nearly 0.7 volts, and in reverse bias condition there is no chance of flowing, and in reverse bias condition the P-N junction does not conduct. But when the voltage is provided for a certain interval, of depletion region is being created. In this depletion region, we will observe some electrons present in this boundary of the P-N junction towards the P side, and we will see some holes present in the boundary of the P-N junction towards the N. Now when this depletion region gets created, a very small amount of current flows in reverse biasing condition, and at that point it is called the breakdown voltage, and that current is called, you could see a very low amount of electric current passing in the reverse bias condition, and that is called reverse saturation current. Now observing the voltage and current characteristics of a diode. So the VI characteristics of a diode represents in this plot. Here you could see the y-axis is the current axis and the x-axis is the voltage axis, and the red one we could see the forward bias region and the green one is the reverse bias region. So we could see this gradually when voltage is applied through a diode in forward bias condition at 0.7 volts, it picks up. So it shows that when a P-N junction or a diode is in forward bias condition, it does not start sharply from 0.7 volts rapidly. It takes some time to reach to that level. Theoretically, we said that at 0.7 volt, it gets up the there is a voltage. In theoretically, we said that at when there is 0.7 volts of voltage drop is occurred, then the diode starts conducting. But in practically, it takes some time to drain that 0.7 volts. It is not drained directly. But in reverse bias condition, we could see that, as we said in the previous topic, it does not conduct till a particular point of voltage. When that breakdown voltage is reached, it starts conducting. So this equation form of this forward bias and reverse bias condition will be explained to you in another subject called physics of the semiconductor devices. But though this is basic electronic circuit, basic electronic engineering, only a mere concept regarding the VI characteristics of a diode is given. After using these characteristics, we'll move on to the circuits where diodes are implemented. For example, the rectifier and the clippers and clampers, etc. So friends, at the end of this lecture, let us discuss what else we have completed till now. So we have completed the introduction to semiconductors, the junction diodes, the principle of diodes, and the voltage current characteristics of the diode. So in the next class, we will be studying about the equivalent circuit of diode, the AC analysis, equivalent circuit of the diode, and we will also see the behavior of diode when a AC voltage is being given to it. We will see it in multisim. Today we have already discussed the breakdown mechanism of the diode. So in the next class, we will understand the different aspects of the diode under AC voltage, where we will analyze the plots in multisim as well as in equation or in theoretical form. So if you find this video informative, please hit the like button, and if you have any doubts, please write it in the comment section and subscribe the channel to stay connected with us for more information, more videos and more lectures. Thank you.